Imagine a world where car batteries are assembled by biological organisms. They are non-toxic, biodegradable, and very powerful. Step into the world of Dr. Angela Belcher. She walked on this beach during her college years at UC Santa Barbara on the few days when she wasn't busy getting degrees in chemistry, biochemistry, molecular biology, and electrical engineering. This is where she got her inspiration for a radical line of research that could change batteries forever.
So when we're thinking about how to make new technologies, we're going to look at it from a very new perspective. 500 million years ago, when the environment of the ocean changed, organisms that were soft body organisms didn't make hard materials, didn't make shells. But through selection pressure and through changes in the chemistry in the environment, they learned how to make materials like shells.
Only a multidisciplinary mind like Angie Belcher's would look at that and think this.
And we said, wow, if organisms could make shells, I wonder if we could get organisms to make batteries.
The idea of teaching organisms to make batteries seems out of this world. But Angie Belcher has found a way.
The reason that it's such a special structure is it's based on nanotechnology.
Nanotechnology refers to one of the smallest units of measurement, the nanometer, a billionth of a meter. Like the abalone shell, Angela Belcher wanted her nano batteries to harness the power and perfection of biological systems.
I isolated the proteins that are involved in making the really exquisite structure of the shell. And by looking at the periodic table, I started thinking, well, what about all these other elements? Can these same proteins that work for shells, can they work with other kinds of elements? And in fact, it was pretty amazing they could work on other kinds of elements. So what we had to do was pick an organism that was easy to manipulate and could be propagated on a very short time scale, so we picked viruses.
The virus, it usually makes you think disease. But in Angie Belcher's lab, it's a hard-working green machine.
And then we actually start with about 1 billion viruses that are all genetically identical to each other.
Even though the viruses are identical, they have minute differences, the same way identical twins can look and act differently. What Angie Belcher and her students need to know is which of these viruses will bond with a metal oxide material. That's what makes them conduct electricity. Out of 1 billion, only a tiny handful will succeed.
Now these are the winners. These are the ones we're going to keep and test to be able to grow our electrode materials. We take those and we isolate them.
These winners are taken for a ride down to Dr. Paula Hammond's lab. Here, they'll work 24/7.
We can build very, very thin films simply by taking one material which has positive charge along it and another material which has negative charge.
The beauty of this virus is that if you put it near a sticky surface, it begins to organize itself in rows. Like bricks and mortar, the viruses stack themselves. Pretty soon, they've built a solid plate. This is the plus side of the virus battery. On the other side, a different virus builds the negative plate. To finish off the battery, tiny wires are attached.
And this is the final product, an ultra-thin, ultra-lightweight, fully water-based virus battery. This is very exciting. Being able to build a high-capacity lithium battery allows us to not only look at green approaches to building these battery systems, but also enables us to make extremely thin films, which then provide promise for micro batteries and large-scale macro batteries, which can be rolled up, have very light weight, and be used for portable products.
This is a lithium-ion rechargeable battery. Now, there's other advantages in the fact that once we have the right sequence, we can make millions, millions, and billions of copies of it, and every time we make it, they're exactly the same, and they'll self-assemble into the structure.
It's amazing what you can figure out when you spend a day at the beach.
If you think about how abalone makes shells, they don't use any toxic materials. And when the abalone dies, they don't add toxic materials back into their environment. To us, that's a wonderful pattern to follow.
One day, Angie Belcher will test thousands of these batteries in a hybrid car. But already, a new breed of battery is taking the plug-in hybrid to 3-digit mileage.
We go from a 25 mile per gallon car to a 100 mile per gallon plug-in hybrid. And that's an enormous reduction in the amount of consumed gasoline.
Dr. Yet-Ming Chang is the master of battery power. His kids sometimes wonder why their toys move so fast. But it's not all child's play. Yet-Ming Chang is developing a battery that will help a plug-in hybrid get over 150 miles to the gallon. Just think what that would do to your gas bill. Today's hybrid electric cars use nickel metal hydride batteries, but they're expensive and bulky.
You don't want to lose your trunk space, and you can't add weight to the car.
And they can wear out in just a few years. When Yet-Ming experimented with lithium-ion batteries, like the ones in laptops, he discovered why they wouldn't work in a car. They can short-circuit, heat up, and explode.
Unacceptable for the vehicle market. We started looking at a class of battery materials called olivines. Olivines are actually a class of minerals that are widely found in nature, the geological minerals.
But in the lab, he broke them down into tiny particles and added metals like aluminum and zirconium.
In experimenting with those materials, we made this discovery that we could get very high charge and discharge rate capability out of this material.
The result was a particle that would pack very tightly inside the battery, creating lots of potential for electric charge. To test his material, Yet-Ming Chang has to go to the glove box. With toxic, highly flammable chemicals, he's going to make a new generation of lithium-ion batteries.
And now I'm going to assemble the cell here, and I'll do so using this pair of tweezers. Now what I'll do is to take out this positive electrode and lay it right on there like that, and now I'll add the liquid electrolyte.
He removes the battery to test it in his lab.
This is one charge-discharge curve for a test cell like I just assembled. And what it shows is the voltage on the vertical scale. And here's 3 volts, here's 4 volts, 2 volts down here.
His battery can discharge itself in seconds, which means it can deliver power fast. That's what cars need.
This is called a 26650 cell. And it's a little bit bigger than a D cell.
But electricity runs through it like lightning. It is 10 million times more conductive than the previous lithium-ion battery.
The key thing is that it can supply enormous power.
To see that power in action, take a look at the kilocycle.
The kilocycle is roughly the same size and weight as a conventional motorcycle. It has a battery pack and an electric drive system. And it's designed for the quarter-mile drag strip race.
What you're about to see is a test of the power delivered by Yet-Ming's latest batteries.
The 0 to 60, about 1.4 seconds. Towards the end, as it's nearing the finish line, is that you'll see this, essentially a fireball. The battery supplies so much power that it's destroyed the motor. It sent the motor up in flames.
Not great for the motor, but it's a new milestone for battery power.
For every one of those drag strip runs, the kilocycle only uses about a nickel or a dime's worth of electricity. And so even though it's a demonstration of power and not fuel efficiency, even there you start to see the benefit from fuel efficiency.
With this discovery, Yet-Ming Chang plans to revolutionize the car industry. Already, he can get more than 150 miles per gallon in his plug-in hybrid.
A fully charged battery allows me to make the round trip to my home in Framingham and back to work the next day, and I end up using about a third the amount of gas. In terms of the dependence on foreign oil, that's an enormous reduction in the amount of consumed gasoline.